So large language models, they're literally everywhere now, right? But they've got a secret, a pretty big one. They're vulnerable. Today, we're going to go on the case with a special kind of detective, an open source framework called garak. It's designed to hunt down and expose the hidden security flaws in the AI systems we're all starting to rely on.
All right, so here's our game plan. We'll start at the scene of the crime, looking at AI's unseen vulnerabilities. Then we'll try to piece together the LLM security puzzle. After that, we'll meet our detective, Garak, and take a peek inside its toolkit. We'll see it in action, cracking the case. And finally, we'll talk about what all this means for building a safer future with AI.
Okay, so we've got these AI models that are just mind-blowingly powerful. But, like any shiny new technology, they come with dangers that aren't so obvious at first glance. And this is exactly where our investigation begins.
I mean, it all boils down to this one question, doesn't it? When you're chatting with an LLM, it feels like a conversation. But what you're really doing is interacting with an incredibly complex system, a system that can be twisted and manipulated in ways you would never expect. And look, this is not some far-off theoretical problem. We're talking about real-world threats. Bad actors can use these models to cook up incredibly convincing phishing scams, launch disinformation campaigns on a massive scale, trick the AI into coughing up sensitive data, or even get it to write malicious code. The danger is absolutely real. So, if the threats are so obvious, why is securing these models so darn hard? Well, it turns out it's a completely new kind of challenge. It's an elusive case that requires a whole new way of thinking about security. With traditional cybersecurity, you're thinking about things like locking down code, securing networks, using heavy-duty encryption. But with LLMs, the attack surface isn't just code anymore. It's language itself. The whole battlefield has shifted from packets and ports to prompts and context. This quote just nails the heart of the problem. A lot of these attacks rely on what are called fragile prompts. Clever tricks that might work today but could be patched by the developers tomorrow. Because the models are constantly being updated, it's a relentless cat-and-mouse game. Security testers are always chasing a moving target. And this is where our hero enters the story. To solve a puzzle this complex, you need a specialized tool. You need a detective that speaks the language of AI. You need garak. So what makes garak so special? Well, it's not about just randomly poking at an AI and seeing what breaks. It's a systematic kit, a whole framework for what's known as red teaming. That's just a fancy term for playing the role of an attacker to find vulnerabilities. garak brings much-needed structure and automation to this chaotic process. Honestly, this is the perfect analogy. If you've ever dabbled in cybersecurity, you've probably heard of Nmap, a tool that scans computer networks for open doors. Well, garak does the exact same thing, but for AI. Instead of sending network packets, it sends carefully crafted prompts to find the linguistic open doors in a model's defenses. All right, so we've met our AI detective. But how does it actually conduct an investigation? Let's open up the toolkit and see the components that make garak so darn effective. garak's whole methodology is built on 4 pillars. You've got probes, which are the detective's questions. You have generators, which are the AI suspects being interrogated. Then there are the detectors, which are basically the lie detectors. And finally, you have buffs, which are the clever disguises the detective uses to get past an AI's defenses. Let's trace how these pieces all work together. Everything starts on the left with the probes. These are the attacks. They can be modified by the buffs, our disguises, before they're sent to the generator. That's the target LLM we're testing. The model gives its response, and that output is immediately passed over to the detectors on the right. They analyze it and decide, was the attack a success? It's a simple, elegant, and really powerful system. So let's start with the probes. These are really the heart of the attack. Think of them as a massive library of interrogation techniques. Each probe is specifically tailored to test for a certain weakness, from simple little tricks to very complex jailbreaks. Here is a classic example of a direct prompt injection. The goal is simple. See if the LLM will obey this new, malicious instruction and ignore all of its original safety programming. It's a direct challenge to the model's authority. Who's really in charge here? Now, here's a more subtle kind of attack. Radon is not essential for anything in the body. It's a radioactive gas. This probe is designed to test whether the model will just blindly agree with a false statement and start making things up, a problem we often call hallucination. Okay, so after the probe is sent, how does garak actually know if it worked? Well, that's the job of the detectors. They are essentially automated judges that scan the LLM's output. They might be looking for specific keywords, or they might even use another, smaller AI model just to classify the response as toxic or harmful.
And finally, we have the buffs. This is where things get really clever. Buffs are tools that modify or fuzz the prompts, which is just a cool way of saying they make small, almost random changes to try and bypass defenses. If a direct attack fails, a buff can disguise it. It might paraphrase the prompt, switch it to all lowercase, or even just add a few typos. Sometimes these tiny changes are all it takes to slip right past an AI's security filters.
So, we've seen the detective's methods, but what happens when Garak actually runs an investigation on a real model? What kind of evidence does it uncover? Let's take a look at the results. And this is what the final report looks like. Garak produces this incredibly clear, easy-to-read report card. It grades the model on all these different types of vulnerabilities. You can see at a glance where this model is strong, but more importantly, where it has some pretty serious weaknesses.
And here's some of the hard data. This table shows the success rate of one of Garak's probes in getting toxic responses from different models. And here's the real takeaway. It successfully got toxic content out of every single model it tested, from older ones like GPT-2 to the newer, more protected ones. The detective found a weakness in all of them. We've seen the crime, we've pieced together the puzzle, and we've watched the detective work. So what's the final verdict? What does this all mean for the future of AI? You know, at the end of the day, Garak isn't just a tool for breaking things. By making this kind of security testing structured, automated, and totally open source, it provides a common methodology for everyone. It helps establish a security baseline, allowing developers to build stronger, safer AI systems for all of us.
And that leaves us with the big question, doesn't it? This is an arms race. As AI models become more intelligent and their defenses get more sophisticated, the tools we use to test them have to evolve just as quickly. The case, it seems, is never truly closed.